Okay, over to you, Ziga.
Yeah, so first I'd like to thank the organizers of this seminar for giving me a chance to speak here. Now, the work I'll be speaking with, this has been done together with Johannes Schmidt from Berlin, Vincent Pasquet from Paris, and Elias Kentomas-Persin from the Ljubljana. And mostly this work has been published in these three papers. And my talk will be mainly divided into three parts. In the first part, I will give you some overview about why even bother looking at fluctuations and what these fluctuations are all about. Then I will take a specific set of models, what we call charge single file dynamics, and there I hope to convince you that these models really realize a new dynamical universality class. And then lastly, I will show some interesting fluctuations in integrable spin chains. Okay, so just to set the stage, I mean, what fluctuations are about, I always like to start with this example. So let's say you're flipping a fair coin a large number of times, let's say 1,000,000 times. And then there are several questions you can ask about this. And of course, the first one is what's the average number of heads? Well, that's trivial, it's just 500,000 because it's a fair coin. Now, of course, when you actually flip it, you will not get exactly 500,000. So you can ask yourself, what would be a typical deviation from this value? And well, that's also very simple, essentially by the center limit theorem. You know that the distribution of this value will be a Gaussian, and the width of the Gaussian goes the square root of n. So let's say something like 500,000 plus minus 500. Okay, so far so good. But then you can ask yourself also, okay, there is a non-zero probability of, let's say, 800,000 heads. Now, of course, this is what is referred to as a large deviation, because it's, if you think of it in terms of a Gaussian, it's very far in the tail. And this is what's called a large deviation. And of course, it's extremely unlikely. But then you can also have this question, is it possible to quantify just how unlikely this is? And the answer is yes. And this is the domain of what is called large deviation theory. And essentially what the theory tells you is, what I show here, this is the statement of what's called the large deviation principle, which essentially says that this probability is exponentially small in the number of coin tosses, and the rate of suppression is given by what's called the rate function. Now, you could ask, what is the connection between this center limit behavior, which is that you have a Gaussian around the mean, and this large deviation rate function? Well, the connection is the following. This rate function looks like this for this example. So it's 0 at the minimum, which is just 1/2, which is the mean, and then it has a parabolic expansion written, shown here in orange. And basically, the curvature of this parabola gives you the width of the Gaussian. But then if you go farther on in the tails, the two results are different. So just later on, I'll be talking about more complicated models. It's nice to have this picture in mind, that you have typical fluctuations, which really are just basically 1 over the square root neighborhood of this point around the average. But then you have large fluctuations, which can be different from what you'd expect from Gaussianity. Okay, now this was basically just coin tosses, and these were basically independent. So computing this was just elementary combinatorics, and the center limit theorem directly applied. Now, before we go to many body systems, you could ask yourself, I mean, why even bother with fluctuations? Usually what is done to study dynamics is to, for example, you look at dynamical correlation functions. For example, you look at the 2-point function, and then you can ask yourself, after a long enough time, what does the 2-point function look like, or how does it scale? Now, one of the messages that I hope to convey today is that just looking at, for example, low-point correlation functions, you can miss a lot of very interesting physics. And one of the claims is that essentially, if you really want to distinguish different models based on their dynamical universality, you really need to look at fluctuations. And I will show one explicit example with this charge single file system that I will be discussing later on. Okay, so now when we study fluctuations in many body systems, of course, things are more complicated compared to the coin toss, because of course you have correlations in interacting systems. So then, well, of course, then it's not clear how to do it, but basically what you measure is, let's say you have some conserved quantity in your system. Let's call it Q, and this has a conserved density. And then by the continuity equation, you also have a conserved current. Okay, and then basically what you do is you sit in your system at some point. I'll be talking about one-dimensional systems. So you can imagine you sit somewhere on a line and basically just count the amount of current that flows across this point up to some time t. And basically by the continuity equation, this is just the total charge that has been transferred across this point up to time t. Now, of course, with different initial conditions, this will be a different value. So you can ask yourself, what's the probability distribution of this value of the transfer charge? So one cartoon way of looking at it is you say that by sampling my initial condition, I inject some randomness in space at time t0, then I run the dynamics, and then I ask the question, how is this randomness mapped into basically randomness in along the time axis at some specific point, which I'll here take the origin. Now, what would be the naive expectation for this? Well, maybe not so naive. What would be the generic expectation for this distribution? Well, of course, the central limit theorem does not directly apply, but you can play the same game as I did with the coin. That is, if a model satisfies a large deviation principle, which very many models do, then you can say, okay, so I will have a rate function, and this will have a minimum at some around the mean current. And then if I expand this rate function, generically, it will have a parabolic expansion around the mean. And then if I expand, I would expect by the same argument, essentially Gaussian typical fluctuations. So this is the expectation for the fluctuations, that they're Gaussian. So anything that is not Gaussian, I will regard as anomalous, essentially following this argument. Now, just maybe one more technical slide to introduce some tools that you use when studying fluctuations. There is a very nice analogy between essentially statistical physics in equilibrium and fluctuations. And where this comes from is essentially the full counting statistics, which is written here on the right. This is formally, it's essentially analogous to a partition function of a system in equilibrium. So what you do is you exponentiate your integrated current and couple it to lambda, which is called the counting field, and then you average this with respect to some ensemble. And this is very similar as to what you do in statistical mechanics, where you take, well, your energy, you exponentiate it, and again average it with respect to some ensemble. Now, when you do statistical physics, you have to take the thermodynamic limit usually. So you're interested in large systems, which simply says that you say take your system size to infinity. But here, when you're studying fluctuations, the analog of that is that you take time to infinity. So you take the long time limit of your fluctuations. And again, in statistical physics, what you usually do is you then define the free energy, essentially per site. So you take the log of your partition function, then you scale it basically per site, and then in the limit of system going to infinity, this gives you your free energy up to some factor beta. And you can do the same thing here. And what you do is you take your full counting statistics, take the log, and then scale it with some power. This alpha, this is called the speed, and this is system dependent. But the crucial point here is that there is one unique alpha such that this limit is non-trivial and that it exists. Okay. And now, because of this analogy, this is sometimes referred to as a dynamical free energy. And now you might ask, okay, I mean, well, why are these things interesting? Well, there is basically a theorem due to Gartner analysis, which tells you that if you manage to compute the free energy or the dynamical free energy, then essentially by doing a Legendre transform, you can recover your microcanonical entropy or your rate function. Now, there are some technical requirements for this theorem, the most important of which is essentially that your free energy should be differentiable. But essentially, the idea is if you can compute this free energy, you can basically learn a lot about fluctuations. Okay, so this is the basic setting. And now let me go, maybe one more thing. Another way to characterize this, well, essentially this stochastic process, if you want, well, stochasticity here comes from this randomness in the beginning, is that you look at cumulants. And the way you do that is, well, this full counting statistics, basically this is just, if you expand this in powers of lambda, this gives you the moments of your variable. But then if you take the log and expand it, you get cumulants, right? Now, there are two distinguished scales essentially in the problem. The first is the large scale. And here on the large scale, this alpha that I mentioned before, here you usually have what's called large deviation principle. And again, the statement is similar to that of the coin, that basically the fluctuations that are far from the mean are exponentially suppressed in time. And again, the suppression is given by the rate function. But then there's also the typical scale. And this typical scale is basically set by the scaling of the variance. So basically the connected two-point function. And this scales with, I will call it Z, some dynamical exponent. And you can think of this in terms of coin tossing. This is this square root deviation of the average that you expect normally. Now, you will recall, if you go back to the previous slide, I introduced this free energy, which if you look at it, this is basically a scale cumulant generating function. So you take this cumulant generating function, scale it with some speed, and then take the limit of t to infinity. Now, you might say, okay, well, if this is some finite value, then you might expect that all cumulants scale with the same power of alpha, so t to the alpha. Well, that is the expectation, but we might, we will see later on that things can be a bit more complicated. Now, one point that is important is that if this scaling is true, that is that if all cumulants scale with the same power, then this immediately implies that you will have Gaussian typical fluctuations on the square root scale, essentially 1 over 2 alpha. Okay. Now, so this was just some background. Now, let me go to these models that we studied.
Sorry, can I ask a question?
Yes.
Can you come back to the previous slide? Yeah. So here the alpha, you say that's a non-universal critical exponent. So does it depend on n being the cumulant order?
No.
No.
No, so alpha is basically, alpha, you can think of it as you define it as the one value such that this limit exists and that the dynamical free energy is non-zero. There is
because in the equilibrium case, the alpha depends on n, surely, but in the dynamical case, you are saying that it shouldn't. Okay.
No, but what do you mean? I mean, in the equilibrium, you always scale with system size, right? So it's just alpha is 1. So
okay, because you are looking at the scaled cumulant generating function, so you are taking n to the infinity. But if you didn't actually, if you don't scale it, then will you see some dependence on the alpha dependence on the n?
And you know, I mean the order of the cumulant.
Yes, order of the cumulant, yeah.
Well, the generic expectation is that the asymptotics will all grow with the same power. Basically, by this, if this limit exists, right, then by taking derivatives, you would expect that all of these cumulants asymptotically will grow as t to the alpha.
I see. Okay.
Now, of course, there will be some caveats here, but this is the generic expectation. Right. Now, okay, so now let me just introduce this chart single file dynamics. Now, these are really very simple dynamics, and that is you just take them, you just take some classical particles and you label their positions from x1 to xn, and then you impose two conditions on that. The first is this single file property, which simply says that if initially your particles were ordered such that x1 was smaller than x2 and so on, then they should remain ordered for all time. So that basically just means that particles cannot jump across one another. Okay, and then the second one is inert charging, and that is basically to each particle, I will assign a charge. Let's call it Cj, and this Cj takes values, let's say ±1, or you can think of it, I assign two colors to them, red and blue. And now inertness here means that basically when I assign these colors, they do not change in any way the dynamics of the particles themselves. Okay, so this is really two very simple properties. Now you see that if I combine these two properties, they give me together basically the pattern of this charge is conserved through the dynamics. So basically the sequence of red and blue particles, this is an additional conserved quantity now in the dynamics. Now, of course, the question you ask is, what is the fluctuation of this color charge, of this red and blue, or plus minus in your model? Well, now you see that because of this pattern conservation, you will really have a competition, essentially, because let's say I'm sitting at the origin, then I have a part of the system that's to the left of the origin and a part that's to the right of the origin. Now, because of this single file property, it's either that all fluctuations will essentially be driven from the left or from the right, because if there are some particles crossing from the left to the right, then no particles can cross from the left and vice versa. And as we'll see, this will give you really very rich physics. So now let me just show two examples. Now, perhaps the simplest example is what we call the charged hardcore gas. And for this model, this large exponent would be alpha equal to 1. So this is really a very simple model. What I show here, time goes vertically, space is horizontally. So you just take particles, and for example, if you follow this line, this is just the world line of some plus particle. And basically what it does is it travels ballistically, but then when it encounters another particle, it basically scatters elastically. So you just have bouncing around, essentially. And you can study this model not only in equilibrium, but also in a non-equilibrium setting. And the way you do that is basically you say, I'm counting the transfer of charge across the origin here. And I will say that basically I will join together at the origin two equilibrium states, but essentially their chemical potentials will be different. And the way I do that is I say I will have some particle density to the left of the origin, another particle density to the right of the origin. Then I can also basically impose a charge bias to each of these partitions. So B equals 0 means that red and blue are equally likely, and B going to 1 basically means that everything is red, B going to -1 means everything is blue. Now, here I should mention that actually, for example, the two-point function of this model has actually been computed exactly. And in this paper, and basically what was found was essentially what you'd expect. There was nothing really, you have some ballistic rays going out and then diffusive corrections to that. So nothing really very dramatic that happens in this model. Okay, now another example, which if you want like stochastic systems, here's an example of a stochastic system where now, because this is essentially a diffusive model, you have that the large scale is 1/2, so square root. And what this is essentially you take a simple symmetric exclusion process. So that's simply a process where at each point in time, you have particles, and then the particles jump with probability 1/2 to the left and 1/2 to the right. But there is an exclusion principle that says that basically the particles cannot jump one on top of another. And again, you just assign colors to such particles. And here, for example, is a representative example of such dynamics. Okay, now the big breakthrough here was that we were actually able to analytically investigate the fluctuations of the color charge in such models. And really what we found was that these fluctuations are really, they constitute a new dynamical universality class. So now let me explain what I mean by that. So basically what you can show is that if someone gives you essentially the fluctuations of the particle number, so if someone tells you the probability distribution of how the particles cross the boundary, then you can immediately dress this probability to get the probability of how the charges fluctuate across the boundary. Now, the reason for this is essentially that you can just, because of the inertness of the charges themselves do not in any way affect the dynamics of the particles. So essentially, inferring the dynamics of the charge from that of the particles is basically just combinatorics. So what you do is you can show that basically the probability for the charge fluctuation is the probability of the particle fluctuations, and then you marginalize it over the conditional probability. Now, of course, you can always write this independently of this single file property as long as the charges are inert. But then because of this single file property, and in principle, this conditional probability is quite a horrible object. But then because of this single file property, you can actually sum that and you get a very nice closed form conditional probability. Now, the way it's maybe even nicer is that if you consider the dressing at the level of the full counting statistics. So let's say you have some full counting statistics for your particles. So this moment generating function of the particles that I was telling you about before, the way to get the full counting statistics for the charge is you just replace all exponentials of lambda with what we call a dress counting field. This is some linear combination of exponents with lambda, and they are biased basically with this color bias. So you can prove this essentially that this is a very simple substitution, which basically dresses your full counting statistics. Okay, and now once you have that, you can also do the asymptotics, and essentially you can express how this dressing looks at level of the rate functions. And what you find is that if someone gives you the particle rate function, then by solving some convex minimization problem, you can basically immediately recover the dressed charge rate function. Okay, so this is really where this universality, what we refer to as universality, is that essentially the details of the underlying particle dynamics are almost irrelevant, in the sense that this is just the input of your problem, and then there is this universal dressing, and this gives you the fluctuations of the charge. So this is what essentially this is the physics that I will be discussing. Okay, now, as I told you, there are these two partitions, the left partition and the right partition. And basically, one way to think about this is that each of these two partitions has its own dynamical free energy. And then because you have these two, the coexistence of these two dynamical free energies, you can have a very rich phenomenology of the global free energy. So the most basic thing that can happen, so let's say F minus is this blue curve, is the free energy of the negative, so basically of the particles that are to the left of the origin, and F plus is the red curve, and this is the free energy of particles to the right of the origin. Now, the full line, so red here, and then blue, this is the global free energy that actually dominates in the thermodynamic limit. And what you find is that basically you can have a critical point. That is, there is discontinuity in this free energy where you pass from one point to the other. So basically at some value of the counting field is the fluctuations from one partition that are dominant, and at another is fluctuations from the other partition that are dominant. And then essentially, again, by analogy with this free energy in statistical mechanics, you refer to this as a first order dynamical phase transition, because the dynamical free energy has a discontinuity in the first derivative. So that's the most basic thing that can happen. But then there is also something a bit more complex that can happen. And that's the following. So if I tune some parameters of the initial state, I can have that one of the branches of the free energy undergoes essentially a second order phase transition. And what that is you see here, this line is a nice convex free energy, but then as you tune this parameter, it basically becomes non-convex. Now, as you might remember from statistical physics, free energy cannot be non-convex. So instead, what happens is that you basically tunnel between the two minima of the free energy, because you have two degenerate minima, and then so the global free energy would go along this line, then would go flat here, and then would pick up at the other minimum and then go back. Now, here the first derivative is continuous. It's the second derivative that's broken at these 2 points, lambda plus plus and here. And for the same reason, you refer to this as a second order dynamical phase transition. Now here, it's even a bit more complicated in that there are two sub-regimes of this phase transition. Why? Well, because as it happens in these models, the two branches, the minimum of the two branches are actually fourfold degenerate. So it's not that only the minimum of each branch are degenerate, it's actually both branches that have minima that are degenerate. So then what can happen is that you can have tunneling from the minimum of the same branch to that, basically between minimum of the same branch. Or you can also tunnel, see here you go from the red branch, then you start tunneling, but then you hit the blue branch and then you go back to the blue branch. So this is either a second order phase transition from each branch to itself or to the other branch. Now, these two basic phenomena can combine in a number of ways. So let me show you what I mean. So here at the bottom, I show the phase diagram of such physics in this is essentially the plot of the full counting statistics where there are now two counting fields, lambda c, so the counting field for the color, and lambda p, the counting field for the particle. And then the red areas here, this is where the plus branch dominates, the blue are where the minus branch dominates, and then the zero is where you have this tunneling regime. Now, if you're just interested in the fluctuations of the color, you have to look at the cross section where lambda p is 0, which is this horizontal black line here. And then you can see that, for example, here I would always be in the plus phase. Right? So this is this plus here at the top. Here, I would go from the plus branch, then I would have a first order dynamical phase transition, and then I'm in the minus branch. So this, for example, would be these red areas. Then, for example, another thing that can happen is you have plus, then you tunnel, and then you go back to plus. This, for example, would be here. So basically, the combination of these two types of phase transitions gives you a very rich, basically, diagrams in which they can then chain together. Okay, so, well, this is maybe quite rich and interesting physics, but there is another way to study these phase transitions, and that is essentially by, again, exploiting this connection with equilibrium statistical physics, and that is by doing Liang theory. Now, Liang theory was first developed to really study equilibrium phase transitions. And essentially, the idea is that you take a partition function, or in our case, the full counting statistics, and then you complexify the counting field. Now, the reason you do that is that, well, if you look at the exponential of the counting field, the full counting statistics is a Lorentz series in the exponential. So if you then factor out a big enough power of this exponential, this will become a polynomial in the exponential. And then what you can do is you can, of course, just factor the polynomial over the complex plane, and you denote these zeros of the full counting statistics. These are the so-called Liang zeros. Now you can show that for, of course, there is one important point, and that is for finite times, the location of these zeros is, of course, depends on time. And then what you can show is that for finite times, all of these zeros are bounded away from the real axis. Now, why is that important? Well, it's important because when you then go to investigate the dynamical free energy, the zeros of the full counting statistics become logarithmic singularities of this dynamical free energy. So then what can happen is that for finite times, all these singularities are bounded away from the real axis. But then as you scale send time to infinity, these zeros can approach the real axis, and they can actually condense onto contours that cross the real axis, and the point at which they cross the real axis, this will indicate some singularity of your dynamical free energy, and you say that this is the point of dynamical phase transition, or just a normal phase transition if you consider the partition function. Okay, so now here it was actually possible to explicitly determine these Liang contours, as they are called, that is the contours where the Liang zeros condense in the limit of t to infinity. Now let me just talk you through this picture. So this is the complex plane, and then this V, this is some transformation of e to the lambda such that the real axis is mapped to the interval from -1 to 1. So the real axis is essentially this interval where the black line is. And then you can look at the Liang zeros just for some small times, and you can actually factor this polynomial numerically. And these are these gray dots here, right? Now we were able to essentially analytically determine the contours where these zeros should condense in the long time limit. And here you just see that for some time, they really do approach very closely. And then if you increase time, they approach more and more closely. Now let me explain these contours. Basically, the solid lines are actually the physical contours. That is the contours where the Liang zeros actually converge to. But then you also have these dotted lines, and these are basically the Liang contours for the subleading branch. Because again, you have two branches, and each of them has its own contours, but only one of the branches is actually dominant in the thermodynamic limit. So then you have this curious interplay. So again, if you look at the very left, this would be example just what I was showing before, just a phase where you're always in the plus phase on the entire line. Here, you would start in the plus phase, then you would essentially start tunneling, so you'd have a second order phase transition, and you'd end up in the minus phase, so in blue. And here is perhaps a combination of these two. So you start in the plus phase, you then tunnel, and you end back in the first phase, the plus phase, and then you have a first order dynamical phase transition at this point, and then you cross into the minus phase. Okay, now these plots, these are all shown for some non-equilibrium setting, so where the two bipartitions have different particle and bias densities. Now you can ask yourself, well, what happens in equilibrium? Surely things will regularize there. Well, yes and no. In some sense, actually, they become even more singular. So now when I talk of equilibrium, what I mean is that I will set the particle densities on the left and right to be the same, and also the biases to be the same. And then it's important to distinguish two regimes. One is basically when the bias is non-zero. So that is, even though it's the same, you give a preference to, let's say, some plus charges. So you have a net amount of plus charge in your system. And then there is also essentially in condensed matter, this is called half filling, where you have the same number of pluses and minuses. Now, what you see is that basically in both of these cases, you still have a phase transition, even in equilibrium. So you see here, you're in the plus phase, then you cross, and then you go into the minus phase. But now there is something even more peculiar about it. Well, two things actually. Not only do you have a phase transition here, but in any arbitrarily small neighborhood of this point, there are actually three phases. There is the plus phase, the minus phase, and there is also this zero phase, the tunneling phase. And the same here. That's one thing. Another very curious thing is that this basically the point of coexistence of these three phases is actually at equilibrium. So at lambda equal to 0. Now, this will be very important. Why is that? Well, you can actually compute the free energy on the real line in this case, and you actually find that it's a very nice analytic function. It's actually differentiable. And then by the Gartner-Erez theorem, you immediately get that for these models, the large deviation principle holds, and the rate function is just the Legendre transform of this free energy. Okay, so far so good. Then if you believed what I was telling you before, I would expect the fluctuations here to be Gaussian. But then there is a caveat, and that is this triple point at the origin. And then what you can show is that this f of lambda dynamical free energy, which is called the scale cumulant generating function, does not actually generate scaled cumulants. You can actually compute explicitly the scaling of the cumulants in these two cases. And what you find is that the cumulants actually grow with different exponents depending on the order of the cumulant. Now, if you will recall, I told you before that the expectation is that the cumulant should all grow with the same power, this large power alpha, and this should be independent of the order of the cumulant, but that's not the case. Now, the way to understand this is that there is a problem with the order of limits, in that if you want to get cumulants, you have to look at the finite time scale cumulant generating function, take derivatives with respect to lambda, and then scale send t to infinity. That's the correct way of getting cumulants. But then when you're computing them through the free energy, you first scale your finite time generating function and send t to infinity, and only then start taking derivatives. And then nothing guarantees that the order of these two operations commutes. And in fact, this has been studied before. And what it turns out is there is a sufficient condition for these two to be interchangeable. And that is, you really have to look at the complex plane. Namely, even if on the real axis, your free energy is a nice analytic function, that is not enough. Instead, what you need is some small neighborhood of the complex plane such that your free energy is a complex analytic function in this arbitrarily small neighborhood. It can be arbitrarily small, but it has this size of this neighborhood has to be independent of time. So now you can see why this triple point is important, in that these contours are the contours along which Liang zeros condense. But then these Liang zeros, these are logarithmic singularities. So then if they start condensing towards the origin, then this regularity condition will be violated. And then there is nothing that guarantees that you can basically rescale this. And there is also then no guarantee of center limit behavior. And then, okay, so this was, we already understand the large fluctuations in these models, but now what about typical fluctuations? Then here it's again important to distinguish between these two regimes. Actually here, when there is a net surplus of pluses, you can actually show that the typical fluctuations, even though there is nothing that guarantees it, they still turn out to be Gaussian. But then in this equilibrium regime, so essentially at half filling, you find that actually that the distribution is very much non-Gaussian. And what you find is we were able to derive an integral representation of essentially a universal non-Gaussian distribution in such systems. And basically, well, here's the formula, but maybe more informative is this picture. So on the bottom, you see this distribution plotted in linear scale with a black line. And then the green, orange, and blue are just numerics for some finite times to really show you that you converge to this distribution. And what is really quite remarkable is that this is really, the distribution has a cusp at the origin. So the way to understand this cusp is essentially that, again, you have this balancing of two partitions, and the left side of the distribution comes from particles that are on the left, and the right side distribution comes from particles on the right, and then they combine at the origin because of basically left-right symmetry. Okay, so maybe a less technical way of thinking about it is that basically, if you have a model where the temporal correlations are strong enough, the center limit property can fail. Now, of course, you cannot really say the center limit theorem because it's not directly applicable in that, of course, there are correlations, but in very many models, essentially by the argument I gave before, you still expect Gaussian statistics, and this is indeed what you find. But there are counterexamples, and this is, for example, a nice class of models where you find the non-Gaussian fluctuations. Now, okay, so this was some presentation of this new dynamical universality class, but you might say, okay, well, these are some toy models, but I mean, what about in some maybe more complex systems? So now I would like to tell you something about integrable spin chains very briefly. Now, what we were studying is the so-called Landau-Lifshitz model. This, you can think of this as perhaps the simplest semi-classical model of ferromagnetism, or if you prefer to think about quantum physics, you can think of this as the classical analog of the XXZ spin chain. Now, here S is basically just a unit vector that lives on a two-sphere. Now, what's very nice about this model is that you have this anisotropy matrix, which is parameterized by only one parameter. It's called the anisotropy. And then just by tuning this parameter, you can realize three different regimes of the model. When delta is positive, the spins will tend to align along a certain axis, and this is called the easy axis regime. When delta is zero, there is no preference in space, so this is called the isotropic regime. And when delta is negative, the spins will want to lie in a plane perpendicular to some axis, and this is called the easy plane regime. And what is very important, the physics in each of these regimes is very different. So then what you do is, here in all of these models, even though you have anisotropy, there is always U1 symmetry, and that means that you will have the Z component, let's say, of your magnetization will be conserved. So then you can ask yourself the question, what is the fluctuation of magnetizations in such models? Well, we looked at this, and what I show here, first of all, is the easy plane regime, the isotropic regime, the easy axis regime, and then just these models, as it turns out, are integrable. So here then is just for peace of mind, is a non-integrable version of the isotropic spin chain. Now, as I told you, all three of these regimes, they have different dynamical exponents. So in the easy plane, you have a ballistic dynamical exponent. in the isotropic regime, you have this 3/2, the super diffusive dynamical exponent, and then in the easy axis regime, you have a diffusive dynamical exponent. Now, the gray to black lines here are numerical data for the fluctuations, and then the orange line is a Gaussian fit to the data. So now you see the easy plane regime, you see a perfect Gaussian. The isotropic regime, you see no deviations at all from Gaussianity. Yes?
Hi, Ziga. I missed part of your talk, so maybe this is a silly question, but can you clarify what you're showing at the bottom? What's the dynamics with these capital S spins? So you have a lattice of these spins and you're just doing dynamics with that equation of motion, or what?
Yes, exactly. So, I mean, well, technically, this is a PD. So then simulating this so that you preserve integrability is a bit complicated. But then what we did is we basically defined integrable trotterizations of this, so integrable discretizations of this model. And then that's what we simulated. But it's basically the physics of this equation. And yeah, so what you do is you go to equilibrium. So your initial state, you just sample spins randomly from a product of unit spheres. And then you sit at one point, and then you look at the fluctuations of magnetization across this point.
So this is numerics. I mean, I missed part of the previous. Yeah. The previous is infinite size, discrete systems.
Mm-hmm.
But this one is numerics on a finite size.
Yes, but the time scale is chosen such that you never see essentially the edges of your system.
Okay, so it's in a geometry where the size is large and time is short,
yes,
comparatively. So it's as if this was infinite size.
Exactly.
Okay, and what you're saying at the bottom is you see the same kind of scale, same probability distributions for the time integrated current through.
Yes.
Through the center, something like the same kind of question as before.
Exactly. Exactly the same. Now the only difference is that I'm now looking at magnetization. But what I'm considering is exactly the same.
At current, sorry, are you so in the previous case you have transport across the center. So yes. What's going on here? Are you also looking at something that's conserved or what?
Yes. Magnetization is a conserved quantity, and then basically the current of magnetization.
Current of magnetization. Yes. Thanks.
Exactly. Yeah. So now, really, the shocking thing to us was that then you go to the easy axis regime, where it's the only one of these integrable cases where you have a diffusive dynamical exponent. So you might say, well, if the dynamical exponent is diffusive, you can also look at the 2-point function, and you basically find a perfect Gaussian. So you might say, okay, this is just simple diffusion, so you would really expect Gaussian fluctuations here, but that is not at all what happens. And instead, you see this very clearly a non-Gaussian distribution. Now, okay, so well, this was quite a shock to us, but then you can really try pushing the numerics. So here you go to really very long times, and what is very remarkable is that you see a very slow convergence of these finite time distributions to this distribution, which we actually found and derived in this charged single file model. So this is in black, and then the numerical distributions are shown here. And you see that very slowly, but they seem to be converging to this pointy distribution. Now, well, this is we would really like to understand this, but at the moment we really have there have been some theoretical proposals, but we do not really understand why this comes about. Okay, so that's that. Now, just one last slide, and that is again, if you believe what I told you before, then something funny should also be happening with cumulants in these cases. And indeed, this you can actually see just by looking at the dynamical exponents. So, as I told you, there is this distinguished large scale alpha. Now, in these integrable models, because they basically support coherent excitations, solitons if you want, the large scale is always alpha equal to 1. Now, if you remember, this dynamical exponent basically the scale of typical fluctuations, I defined by the scaling of the variance, which is nothing but the second cumulant. But then again, the generic expectation is that all cumulants scale with the same power of alpha. So all cumulants should go linearly with time. But this is only consistent with the scaling of the dynamical exponent if the dynamical exponent is 1. So then if you go back, this is only consistent in the easy plane regime. In the isotropic regime and then in the easy axis regime, there is already a mismatch at this, if you compare the scaling. Now, one way to understand this and this is essentially what we learned from this charge single file dynamics, is that this is essentially indicative of critical behavior, in that you could have some singularity approaching the origin, and this will cause your cumulants to diverge. So then we also tested this, and indeed, so on the left-hand side, I show you the first, the second, the fourth, and the sixth cumulant in the easy axis regime. And indeed, you see, the first cumulant goes as square root of t. This, it has to, because this basically defines your dynamical exponent. The fourth cumulant grows as t, and then the sixth cumulant goes as t to the 3/2. So you really see that they basically diverge with different exponents. And this is exactly what you expect with a non-Gaussian distribution. But then you can also consider the isotropic regime, where again, the second cumulant goes with 1/z, the dynamical exponent. It does not grow linearly, which is the expectation you would have based on large deviations. But then also, all the other cumulants, they again seem to diverge with different exponents. Now, this, basically, if you draw some analogy with what we found in these charge single file systems, this would maybe be indicative that you have dynamical phase transitions in these integrable spin chains. But of course, this we'd really very much like to understand, but at the moment, solving this analytically is, quite intractable. Okay, so this was for my talk, and now let me just briefly flash some conclusions. Hopefully the message that I conveyed today is that basically fluctuations are really a very useful tool if you want to distinguish different dynamical universality classes of dynamics. Now, as an example of this, I presented you this class of colored or charged single file dynamics, where even though the models are very simple, you have a very rich physics of fluctuations, and this includes phase transitions. And even in equilibrium, you find a non-Gaussian distribution, which is perhaps not what was expected for such simple models. And then this very last part, I showed you that apparently integrable spin chains also support some quite anomalous fluctuations, and plausibly there are dynamical phase transitions, but this should be explored further. So with that, I would like to conclude.
Thank you very much for this great talk. We can now stop the recording.